Welcome to yet another exciting educational video brought to you by Chrysolite Tutors. So today we'll be looking at MTH 112, definite integrals and the fundamental theorem of calculus. In this video, we'll be looking at understanding definite integrals as area under a curve, evaluate definite integrals using derivatives, antiderivative or reverse differentiation, applying the fundamental theorem of calculus confidently, compute signed areas and interpret positive and negative results, use substitution to evaluate the definite integrals, solve applied problems involving displacement, area and accumulation, and finally handle step-by-step TNMA style problems. So sit tight as we move into this video. If you're yet to subscribe, kindly subscribe to our channel to get more of our content. So we dive in. What is definite integral? Definite integral. Okay, so definite integral is a computation of the net area between curve and the x-axis over an interval. So let's say that interval is A and B. So you see that it's like the area under the curve. So if this is y-axis and this is the x-axis, and you have a curve like this, so you have this point A and this point B. So the integral is actually the computation of the net area under the curve and the x-axis bounded by these 2 points. So by notation, it is written as integral from A to B of the function f of x dx. Okay, so if the curve is above the x-axis, the contribution is positive. Okay, so if the curve is above the x-axis, the contribution is positive. If the curve is below the x-axis, the contribution is negative. And if the function crosses the axis, the integral adds positive and subtracts negative area, producing a net result. Okay, so we're going to be looking at fundamental theorem of calculus. Okay, so for the fundamental theorem of calculus, for part 1, if f of x is an antiderivative of f of x, then d dx of this integral, let me put a bracket here, as bounded by x and a, f of t dt is equals to f of x. That's for the first one. Now for the second one, this first one actually says differentiation an area function returns to the original function. So if you differentiate an area under the function, you get back to the original function, right? Okay, so for part 2, the main working formula, we know that if I have the differential of function of x and you integrate this one, it goes back to function of x, then the area bounded by this function under a to b is equals to, you substitute whatever you have in the different integral of this function, substitute b in it, and also substitute a in it. So you find a difference. So what this one is saying now is that if I have something like this bounded by these 2 intervals to integrate, I will first of all integrate it. After the integration, I will now substitute b for x, or for the variable inside the differential integral for the first answer, then substitute a for the variable inside the integral for the second part. So I'm going to subtract the two of them to get my final answer. So this is how we compute definite integral in practice. So for evaluating definite integrals, I might have a simple polynomial on the board, and it says that we should find the integral of 2x plus 1 dx bounded by these two intervals. Okay, so the first thing to do is to integrate. Integrating means find the antiderivative. So to integrate this, I have 2x raised to the power 2 all over 2 plus x plus c. Okay, I'm not putting c now because I have a limit. So I now put my limit sign and put 3 and 0. So recall, there's a video on simple integration. So we're able to integrate this one. This first term is just about adding, just as a recap, integral f of x dx is the same thing as saying by formula x n plus 1 over n plus 1. Actually, this is nothing. There's nothing here. You understand? So this is the formula for this kind of integrals. Okay, so that's what we did here. The power increased by 1, and you divide by 2. The power increased by 1, and you divide by 2. Okay, so this is also x squared. Okay. Okay, so we get it now. We get it now. So if we are to do this for this, we will just say x raised to the power 1 plus 1 over 1 plus 1, then times 2. There's a 2 already in this expression. So it's the same thing as saying 2x raised to the power 2 over 2. 2 cancels 2. That's why we have x raised to the power 2 left here. Okay, so that's for this one. So we have gotten the integral of this as this. So the next thing we'll do is to substitute x is equals to 3. Where we see x, we put 3 for this whole expression. It's like this. It's like this. 3 all raised to the power 2 plus 3 for the first one minus 0 raised to the power 2 plus 0 for the second one. So this one now I have 3 raised to the power 3 is 9 plus 3 minus 0. So 9 plus 3 is 12 minus 0, which is 12. So 12 is the answer. 12 is the answer. Or you just say the area because it's actually area you're looking for when we have this limit like this, two limits here. So you cannot say area is equals to 12 square units. 12 square units. Okay? Okay, now, so I will look at a case where you have negative region included. So one of the limits is, one of the area bounded is a negative value. That's minus 2 here in the lower limit. Okay, so, and we're asked to integrate this. I'm putting this, just integrate to find a definite integral. So the first thing we do is to integrate this function first of all. You know that it is x raised to the power 3 plus 1 all over 3 plus 1. This will give us x raised to the power 4 over 4. This is the integral of this, right? So we'll now compute the intervals. Okay, so this function is like this. 2 minus 2. So what that means is that I'm going to substitute 2 into this function to get the first term minus, substitute minus 2 into this function and get the second term. So it's written like this. I will say 2 raised to the power 4 over 4, right? Then minus 2 raised to the power 4 over 4. Okay, so I'll compute this one. So 2 raised to the power 4 is 16 over 4 minus 2 raised to the power 4 is also 16 over 4. So this is going to give us 0. So the above area cancels the area below. Net area is 0. So this one means that there is an above area and below area. So the net area is 0. That's why we're having this 0 here. Okay, so we have this on the board, area with function below the axis. So we're asked to integrate this using these intervals, okay, and get the definite integral. Okay, so the first thing to do is to integrate this function. So what I'm having as the antiderivative is x raised to the power 2 all over 2 minus 3x. No, because this first term, x, I add 1 to the power, that's why I have 2 here. And at the same time, the product, the summation of the what I have, I will divide by it. So 2 up as the power and 2 down as the denominator. Okay, so for constant term, the antiderivative is just adding that that variable, which is 3x, which is x. All right, so now having gotten this derivative, antiderivative or integral, I will just put the limits. I will say x raised to power 2 over 2 minus 3x, then my limit is 2 and 0. So what this means is that I'm going to compute this substituting x for 2 for the first part and x for 0 for the second part. So I have 2 raised to power 2 over 2 minus 3 into 2 for the first part. I put a 0, I put a minus here. For the second part, everything there will be 0. Where I see x, I put 0 square over 2 minus 3 times 0. So you see, I just simply substituted whatever I have here into x for the first part, and what I have here into x for the second part. All right, so here we'll just compute 2 raised to the power 2 is 4 over 2 minus 3 times 2 is 6. So this is the first part. Minus second part, everything is 0 because 3 times 0 is 0 and 0 over 2 is 0. So here 2 is 0. So I will now have 4 divided by 2 is 2 minus 6. This is 0 already. So 2 minus 6 is minus 4. So the negative sign here that we're having here means that the graph is mostly below the x-axis. The graph is mostly below the x-axis. Okay, so definite integrals using substitution. So substitution works the same as before, but you must also adjust the limits. So if we substitute here and do the integral, then we have to adjust the limit because the limit here is dependent on x. Understand? This limit is working for dx. Let me work this out. Now this function has two parts. This part that has a composite that has a power. This part and this part that is 2. There's a 2 and there's the dx. So if I come and say let u be this first part, this first inside function, 2x plus 1. So let u be this one. So I know that du dx is the same thing as 2. If I differentiate this, I will get 2, right? And I can now say this du dx is the same thing as du, making the use of the formula, du is equals to 2 dx. So I've gotten it from here, just a matter of multiplying dx by 2, right? So I have du is equals to 2x dx. Now I can see that I can rewrite this one in terms of u, so that this 2x plus 1 is u, and this 2 dx is du, right? But this integral limit will not work because it's referencing x. So I can change the integral limit to reference u. How? I'll come here and say when x is equals to 3, what is u? I'll put it here and say u will be 2 into 3 plus 1, and u is 2 times 3 is 6 plus 1 7. U is 7 for the first part. So then when x is equals to 1, then I'll say u is 2 into 1 plus 1 is equals to, that is 2 into 1, meaning that where I see x, I put 1, right? So 2 times 1 is 2, plus 1, 3. So u is 3. So I will now rewrite this one in terms of the new function u. So now I will put my integral sign, and instead of having 3, this 3, I will have 7. So I put 7 here. And this one, instead of having 1, I put 3 here. Now instead of having 2x plus 1, I have u. u is replacing 2x plus 1, I put the u, it's power 4. And instead of having 2 dx, I put du. So you see, I've transformed this equation, this expression to this expression, transformed completely without losing its identity. Okay, so I will integrate this one. And the integral is u raised to the power 5 plus over 5. So I put that millimeter here, 7 and 3. So what this means is that I'm going to plug in 7 for u for the first part, minus plug in 3 for u for the second part. So we go 7 raised to the power 5 over 5 minus 3 raised to the power 5 over 5. Okay? So they are having the same denominator. So I can say 7 raised to the power 5 minus 3 raised to the power 5 all over 5. Okay? So you can leave it like this unless the simplification is needed. So you get what I mean now. This is the final answer. The final answer. That is, you can just say 7 raised to the power 5 minus 3 raised to the power 5. You compute this one, divide it, subtract it, and get the answer. So I'll leave it here, or you can continue if you need simplification further. So further, we'll do a similar example with the previous one. So I have on the board this particular function. I can come and say, let u be this inside function, simple one, 2x squared plus 1. And the du dx will be 2x again. And it means that du will be 2x dx, right? Okay, so you see that I have x dx up here, and I'm saying x dx here. But this one is a constant that it can come out. It's a constant already, it can come out. So I will write this like this. Already this integral limit will change because this one is representing x. If I'm going to write a new one representing y, u, I will need to convert this one to the u equivalent. So to convert to the equivalent, when x is equals to 4, that's this upper limit, I have u is equals to 4 squared plus 1, right? Which is the same thing as 4 times 4 is 16 plus 1 is 17. So for the first upper limit, the u equivalent is 17. For the 0, when x is 0, okay, then u will be 0 squared plus 1, which equals to 1, right? So the limit is 1 and 17 already. So I'm going to rewrite this one in terms of u. So you know that 4 is mapping to 17, so it has changed to 17, and 0 is changing to 1 for that one. So I have x dx upstairs. So x ds, this is x ds, but there's a 2 in front of it. So I can put the 2, it's a constant. Instead of having x ds like I have here, I'll have du up, right? I have du up. Then I will now say, all over square roots of u. Now that square root of u is okay, so for this to balance out, these two, I might need to put a half outside so that actually to cancel and become as if there is nothing interfering with this particular formula. So normally you have this constant here coming from the question, from this question, but for this to make sense, you put a half outside so that it will cancel out. Okay, so I will be having it like this: integral 1 over root u du. Okay, at this point, I can integrate this one. This one is the same thing as saying integral 1, u raised to the power minus half du. So this is the same thing as saying minus 1 over minus 1, right? 17, then 1. So this difference is minus 3 over 2 over minus 3 over 2. 17, 1. But this one will go up, be 2 over 3 minus u minus 3 over 2, 17, 1. Now, what we will do from here on is to put these limits. So I have minus 2 over 3, right? While I see u, I put 17. Then minus 3 over 2. Then minus, then I put, it's a minus minus. Okay, let me take this up so that we can see clearly. I'll take it up, maybe take it here. Let me take it here so we can see clearly. So from here, this is what I am referencing, right? So I'll put 17 for u, so it will be minus 2 over 3, then 17, it's about minus 3 over 2, then minus 2 over 3, 1, minus 3 over 2. Okay, so this one, there's a plus here, right? Then this one is a power. Okay, so I can do the, for me I can simplify. So I have minus 2 over 3, then I have, this is square root of 17 all raised to the power 3 17 all raised to the power 3. Okay, then my plus this one is 2 over 3 raised to the power minus 3 over 2. Okay, so you compute this and get the final answer. Okay, so for the application of definite integrals, the first application is under displacement and distance. So we see it being used in this displacement and distance. So how do we apply this here? If velocity v t, if velocity is v t, right? Then displacement can be gotten from this function. Displacement is equals to integral with this limit dt. So if we integrate this function under this limit, you get displacement. And total distance will be v to t absolute value dt. Okay, so that's for displacement. Then another application is area under curve. So population growth, we can apply integration. So, and in economics, we can also apply integration. Speed time graph, we can apply integration. And finally, you have mass, charge, flow, density, accumulation. You have mass, charge, flow, liquid fluid flow, and density. Okay, no, probability. How do you spell it? Probability. So this is that the areas where definite integrals are applied. So you can check out some of these under your National Open University material MTH 112. Check out the TMA questions there. Give us a feedback in the comment sections if you have challenges, and I will be here to help you. I hope this video has been valuable for you. I'd like to thank you for viewing.